Hi everyone, today in this video I'll talk about single slit diffraction. So the main equation you need to know for any problems involving single slit diffraction is, it's all in the formula booklets. It's theta equals whatever this symbol is over b. And it is very important that you know what each of these symbols mean. So obviously, well, not obviously, but in physics, this is used to connotate usually the wavelength of light. In this case, this symbol means the wavelength of light in meters. Now, what does B mean? B is the slit width. Let me draw that with a different pen. Slit width. And what's important is that theta, angle of which the first minimum occurs. Now this sounds really wordy, but it's very important that you guys understand what I mean by this. Okay, so let's say that this light goes through, passes a single slit, diffraction, and we see a pattern. I'm gonna draw this pattern right here. This is the central axis, and at the central axis we're gonna have a central maximum. And then there's gonna be a minimum and a secondary maximum. It's gonna tail out. Same for this side. It's supposed to be symmetric. There's a minimum, a secondary maximum, and then it's gonna just tail out. Now what theta means is the angle at which the first minimum over here occurs. The angle at which the first minimum occurs. I can draw that as this. This is theta. And so if you understand what all these symbols mean, it'll be pretty easy for you to solve questions from now on involving single slit diffraction. Another thing I want to discuss is single slit intensity patterns. So let me draw the graph for a single slit diffraction intensity pattern. So we got, then flip this 90 degrees. Nice. We got intensity at arbitrary units. Let's say this is like, let's say this is 1. And this is gonna be angle measured in radians. Normally a single slit diffraction would look like something like this, with a central maximum. It's very wide. And then we got the minimum, goes up a little bit, and then just tails off. Again, it's symmetrical on both sides. Minimum, up, tails off. Okay, it's good enough. It's good enough. It used to be worse. And these are the thetas. Like they're supposed to be the same. Okay, like the distance from minus theta to origin, distance from 0 to theta is supposed to be the same, but my graph is just kind of wonky. That's how you draw a single slit diffraction. Remember, for each primary, secondary, maximum, the heights should be decreasing. Now let's explore. Okay, let me just rewrite the formula so we don't forget it. Theta equals whatever the symbol, wavelength over b. Okay, let's do a thought experiment. What happens if we increase the wavelength? What happens if we increase the wavelength? I'll draw this new diffraction pattern on top of this graph, this axis, and I'm gonna label the new theta, which is the angle at which the first minimum occurs, as theta 1. Okay. If if wavelength increases, theta will increase, assuming that b remains the same. So our thetas will be plotted. Theta 1s will be plotted a bit further away from what we previously drew. And also, intensities are going to start. Intensity at the central axis will be 1 for this new diffraction pattern again. everything's gonna look the same except that this one's a bit wider. This one is a little bit wider. Keep in mind that the intensities for all maxima, in the case where the wavelength, only the wavelength changes the same. So height of the central green and red maxima is the same. Height of this secondary green secondary maxima is supposed to be the same height as this one. I just drew it wrong. The height of this green secondary maxima is the same as the height of this red secondary maxima. Okay, cool. That's easy. Then what if B increased? In the case where B increases, I'm gonna call the theta of this new diffraction. Wait, did I use the word diffraction grading? No, you're not supposed to say diffraction grading. Single slit pattern. This theta, I'm gonna call it theta 2. And in the case where B increases, then theta will now decrease, right? Because B is the denominator. So I'm just gonna rub out this red graph because it's getting pretty confusing. So we have here theta 2, theta 2. But one thing you should be aware of when you're changing the slit width is that if you're increasing the slit width, you're effectively allowing more light to enter. You're allowing a greater number of photons to flow through per second. And therefore, intensity at the central maxima will be a lot greater. Now let's connect the dots. Okay, something like this. Oh god, that is ugly. That is so ugly. Okay, what about the secondary maximas? The secondary maximas will again also have greater intensities because more photons are entering than before. So we're gonna have something like this. And then it's gonna, tail off like normal. And that's about it. That's it for single slit diffraction. Thanks.